Thank you. All right, so and this is a part where magic happens. So, just to continue with the place where I stopped, with the kernel machines, we have this type of optimization problem, and the cool thing here is that we can reduce this infinite optimization problem to something which is finite, and reduce it to essentially solving a system of linear equation with like n by n size, okay? And as I mentioned before, it has been found recently that in some settings, wide neural networks are actually equivalent to kernels. And this is an exact mathematical equivalence, that as the width of neural network goes to infinity, you exactly get solution to a certain kernel, and in many cases, this kernel can be even like written down analytically. So it's a very satisfactory result. Isn't it great? And it turns out that unfortunately, so I'm giving you the bad news. The bad news is that regime misses some sort of key features of what actual neural networks do, as it turned out. And I will describe now what is this that neural networks do. But maybe before that, let me say a few words about emergence, and then I'll bring it back to what emergence has to do with anything. But this maybe was kind of one of the most amazing things that we have, that researchers have observed. And one thing that, like if you, for example, look at this paper with a rather long list of authors from Anthropic, they did the following. They took models, like GPT-3, and they looked at the number, as they increase the number of parameters, they looked at how well they did on certain tasks, okay? And in general, it has been observed, that's not a new observation, of course, it's maybe not terribly surprising, that, okay, giving more data, of course, is always better. Maybe less obvious is that having more parameters is always better, and having more compute is always better. Again, when I say always, of course, you have to qualify it, but generally this is true. Now, look at what happens here, however. Something is quite remarkable. Like if you look at this problem, this is a 3-digit addition, right? So you're asking this neural network to do addition, and you say, okay, well, why would you want to do addition using a neural network? It's rather poor substitute for a calculator. Well, who cares, right? It's an interesting task. Why do we ask people to do addition, right? We teach them in school to do addition. In any case, so you can see that up to some number of parameters, you basically have no accuracy at all. It's 0. It just doesn't do it. And once you pass some threshold, which is about 10 to the 10, so 10 billion parameters, suddenly it does much better. And at about 10 to the, whatever, 11, I guess, or 10 to the 12, it learns very well. Like 80% accuracy for 3-digit numbers is really good. And now I think it's even much better. So you can see this kind of threshold transition. Some looks a little bit like a phase transition, like, you know, at about 10 to the 10 or 10 to the 11 parameters. And that's what is, that's one aspect of what people have been calling emergence. Yeah. I think they just train it on like the Common Crawl or one of those crazy data sets. It's just trained like on everything in the world. Yeah, I think, okay, I'm not 100% sure. I don't know. I would have to check exactly what it is. It may be trained on something else here. I don't know. Yeah.
You probably know this paper, right, about emergence as a mirage.
I will get to that.
Yeah.
It's not.
It's
not always a mirage. It may be a mirage in some. You know, when you see a mirage, like if you're in the desert and you see an oasis, it may be a mirage, but it's not always a mirage.
Okay.
Right?
Looking forward to that.
Yeah.
So, in a neural network, there's the width and there's the length. And you're sort of giving the product of those, as it were, the number of parameters.
In this case, it's just, I think they're just counting. It's just a sum of those. It's just a sum of, it's just a total number of parameters. They don't differentiate when lengths.
Isn't the behavior different in those limited cases?
I think they're increasing the width and keeping, I would rather not say because I don't know. I'm probably going to mislead you. Yeah.
In transformers, it's the layers. It's the number of layers in transformers at least.
But they also increase, I think, sometimes the MLP width, right? So it may be a mix. Yeah, the layers do matter. Yeah, absolutely.
Just so I understand, for the addition, like 10 to the 6 is the number of like possibilities, right? So you kind of expect that. I mean, after 10 to the 6, it would just memorize, right? But it doesn't. Is that?
I am not responsible for this problem. Let me show you another problem, maybe, and then you can grill me on that one. Let me show you this problem because this is actually something which I will get back to this one. This one is. For modular division, you can do modular addition, it doesn't matter. So you give it, and again, I'll discuss the details of this problem in a little bit. But you're giving pairs of numbers, mod like some prime, 101 or something like that. And you're giving 50% of the data as training and the rest as test, okay? And the question is, will it learn? It's not a priori clear that it will learn this at all. It's just trained on this. It's not trained on everything in the world, just these pairs. And the remarkable thing that they found in this paper, this is OpenAI, only 2 years ago. And this is, I think, what is very, very interesting. On the x-axis here is optimization steps, right? They're running gradient descent. On the y-axis is accuracy. And you can see that for about 1,000 steps, after about 1,000 steps, the training accuracy goes to 100%. But look at the green line, which is the test accuracy. The test accuracy is still close to 0, so it's not learning anything. Now, this is like mod 100, so the random guess would be like 1%, right? So it's 100 classes. You have P and Q, right? And you just predict it. If you predict it at random, you get 1%. So that's not exactly 0, it's like 1. But here's what's remarkable. After about 10 million steps, it suddenly goes to 100. So what was it doing all this time? So you can maybe kind of think about it as this, right? Like you have, you observe, the metamorphosis. You observe a little bug, a caterpillar, and this larva then becomes a pupa. Nothing happens for like, a week or 2 weeks or whatever. So from a visual point of view, nothing is happening, and then suddenly the butterfly comes out of it. Well, butterfly doesn't really look like a caterpillar at all. Yeah?
I just want to verify that I understand this correctly. So in this regime where the training loss is reported as 0, in reality, there is some other quantity that is not 0, right? Which you're measuring and on which you're still doing your...
This is very important. This is accuracy. The loss cannot be 0 because you wouldn't be able to train using gradient descent. So the loss is never 0. But it's small. But I will get rid of the loss, I promise. The loss will be 0, but just not with this method. There is some other way of doing this for which the loss is 0. It's like identically 0 throughout the whole process. So whatever is happening doesn't come from the loss. It sounds a little magical, and I think
this is not really optimization. You're already you're only traveling on kind of local minima. only, right?
Yeah, in this case, it of course has to be optimization just because otherwise you wouldn't be able to do anything. But I'm claiming that optimization is not really what's making this work. Yeah. So notice that in this example, I think this is actually kind of accurate example because, like, it's not true, of course, that nothing is happening. Obviously, actually, it's like very mysterious, right? Like the caterpillar somehow liquefies its internal organs, rearranges them, and it becomes a butterfly. It's a very weird process. And you can see, like, if you do an X-ray, you can see that stuff is changing inside or whatever, some imaging process. But if you just look at it, nothing is changing, right? So from a observer point of view, nothing is changing. Of course, if the observer can see inside, they would realize things are emerging. So that's, that's what we would call emergence, right? In some sort of ordinary language, right? Something like this, butterfly emerging out of the pupa. Yeah. I'm claiming something like that is happening here. There is some sort of liquefaction of internal organs or rearrangement of internal organs. I don't know about liquefaction.
Isn't it also the case that this happens in models that are very over-parameterized? And so it could be that what's happening is a lot of other parameters that were not being aligned are getting with the program, so to speak. The more you are at asymptote, you're still training on them, so it's better for generalization or for validation.
Something like that. We will actually see exactly what's happening in that thing. And but what I'm saying is that if you just look at this, you just cannot see anything. And you can say, okay, this is classification accuracy. What about the loss? Maybe you can see something in the loss. We will see in a minute. But let me first take a step back because I would like to set up the problem, and I have to set it up using kernels in sort of my way to convince you that this is, or to try to convince you that it's analogous to this. Okay, so now let's look at a much simpler problem. So modular addition or division is kind of complicated. Let's look at a very simple problem. And let's just set up the following problem. You take 100 dimension, and my function is simply a polynomial of degree 2, which is the sum of the first time 5 coordinates times the next 5 coordinates, okay? Very simple function. It's a quadratic polynomial, and in fact, it's a function of index 2. By this, I mean you just need to know 2 directions. The sum of the first 2 coordinates times the sum of the next 5 coordinates. So you can rewrite it as a projection onto a 2-dimensional space and some quadratic function in this 2-dimensional space, right? Now, you take 4,000 training points from this distribution, and X is sampled randomly from a normal distribution. It's a toy problem. I don't like toy problem. I don't like calling it toy. Nothing is toy. If we cannot understand something, how can it? Or if it's hard to understand, how can it be a toy? But in any case, you use a kernel machine, just like I described, and you get R squared 0.25. Now, if you don't remember what R squared is like the square loss, but it's normalized differently. So 1 is good, and 0 is bad. So it's roughly like 1 minus the square loss. It's not exactly this, but it's similar. So basically 0.25 is not very good. 0.98 is extremely good. So now we see that, okay, I just said that like kernels were so good, but neural network does far better than kernel on this simple problem. Now, this is not really, like for this problem, you don't need GPUs, you don't need fancy machinery. You can run it on your, laptop in like 2 seconds or something, I don't know. We could have done it, like 20 years ago pretty easily. The interesting thing is that like the first experiment is like 5 years old, 6 years old of this type. There recently has been quite a bit of work showing, so this is a multi-index model. Actually, the index is 2 because it's a linear, it's a projection of rank 2 followed by some sort of nonlinear function. And we have seen recently that neural networks can learn such functions. Now, let me sort of maybe give you a little bit more insight into this, what's happening with neural network. Consider a neural network, and this is a neural network of just an MLP, and you can even think that it just has one hidden layer. So what is this? I take the input, in that case, a 100-dimensional space. I multiply by some matrix, and the size of this matrix is d times 100, when d is my number of neurons. And then I apply some sort of nonlinearity to this, and I take some sum of those things. That's it. That's a neural network. You can do it multiple times, but you can just do it one time. It's enough to. One hidden layer is enough for this problem. Now, if you think about what does W1 do, well, let's think about W1 as some sort of filter, right? It takes my data and it somehow filters. And maybe it is useful to think about this matrix W1 transpose W1 because that does some sort of filtering on the input. It refilters input. So maybe a mental model for a neural net would be it applies this matrix to the input and then does some sort of nonlinearity on top of that. Okay. So that's an intuition. I'm not claiming this is exactly right, but it's a good way to think about it. So think about it as some sort of, in this case, I would like to think about it as some sort of low-rank filter. So I'm reducing dimensionality and then doing some sort of non-linear predictor on top of this low-dimensional representation. It's linear. The dimensionality reduction is linear.
So D is less than 100.
No, D is usually bigger than 100, but the rank of this matrix will be small. Or I expect it to be smaller. So actually, initially, when you initialize it, it will not be small, but it will. I'll show you in a second what happens. But before this, let me sort of introduce this mathematical object because that's sort of key for this. And this is what's known as average gradient outer product. So suppose I have I can define it for any function. It doesn't have to be a neural net. Take a function, and suppose I have some data set X. Again, the fact that it's training is not relevant here. At each point, compute gradient of F with respect to the input, not the parameters, the input, and take the outer product of this gradient and that gradient transposed. That's that's a 100 by 100 matrix in that case. And I'm averaging this 100 by 100 matrices, right, over all of my data. Now, you can kind of think, well, what does this measure? And if you think about it, well, at each point, this gradient is just as a projection onto the gradient direction. So if my gradient direction is somehow a line, I expect this whole object to be low rank, right? So you can kind of think, well, what input directions affect response of model F? And if my model has a form f of mx, so think about that. Suppose m is rank 2, as is in that case. Then the span of the things will be in the span of m. So it will be a rank 2 thing. Okay? So if I can somehow get the correct model, the AGOP of that correct model will just be rank 2 matrix. Now you can say, well, this is for some, if it's really like the true model, but I don't know the true model. So that's the question. How do you actually come up with this object for the true model, not for some approximation? But basically, another way to say this, if I take this matrix, then the top eigenvectors of f of mx align with range of m. Okay, span the range of m. Okay, this is, by the way, not a new thing, but it hasn't been really widely used. But it goes back at least like 20 or 30 years, its use of this object. You can kind of think of this as learning as task relevant, which direction actually affect the output of the model. This is very different from, say, principal components analysis, right? Principal components analysis, I look at what variance of the variance of my features in these directions. I don't care about the features here. I just care about the variance of the output. So if you think about it, this is a generalization of principal components analysis. This is a variance of the output. If you actually take this function to be norm of x, this is going to be exactly PCA. So it's a strict generalization of PCA, if you wish. Okay, you can kind of think about it as a point by point, because if you write it locally, this is nothing else but just the first order tail expansion of that function at every point, and you're somehow averaging the things. But let me now, okay, so suppose now we have this object, and let's just look at some examples, and then I sort of make a claim about this. And you can say, like, okay, why is neural network good? Well, let's go back to that example. And I have this neural feature matrix, which I had before. And let's look at what happens after I train my neural network on 4,000 examples. And I compare this matrix and this AGOP matrix. And what I observe is pretty nice. This is my WW transpose matrix, and this is AGOP, and you can see these are actually almost the same matrices, but at least visually they look very similar. And you can see these are small blocks 5 by 5, which corresponds to the first 5 coordinates and the next 5 coordinates, right? That's exactly what you would expect. Notice that these are not really sparse. They're low, they rank 2, but the sparsity actually is 10. So I'm sort of making a distinction to show that this is not quite the same as sparsity. It's like sparsity, but in directions which are not necessarily coordinate aligned. Okay, now let's look at the example. So, okay, I train this neural network, and I'm going to do the following. I'm going to throw out the neural network now. Just keep these 2 matrices, okay? And I will use my data using those things as a filter and train something else on this filter data. Right? So original neural network now is gone. The only thing which remains are these 2 matrices, both extracted from that neural network. And now, here is a remarkable thing. I only have 500 now training samples, so it's much less than before. But look at this. If I use this NFM, which is this one, and I train a kernel on top of it, my R squared is 0.92, which is way better than training kernel on the original one. And with neural network, it's similar. So I get very good performance from much less data, just because I learned these filters. Now you can use AGOP, and you can see you get very similar, even slightly better results. Now, if I don't use any filter at all, kernel fails completely, just has no signal. There is like no signal, not enough. And neural network does slightly better than like nothing, but very badly. So no filtering is very bad. Filtering is good. Now, what if I just keep the first 10 coordinates? Because I know this all, so that would be kind of like sparsity. 10 coordinates is not that good, not enough, much worse than that. Yeah?
So can you think of this as somehow, so the kernel, you write some, so let's say a plus kernel or something like this. Can you think of this input matrix as somehow modifying that kernel?
It's exactly right. Yeah, I will get. It's exactly. So my mental picture is like the following: is what neural network is doing is finding this filter, then it's somehow filtering, and then it's running some sort of kernel on top of that. And somehow all the juice that you're squeezing from a neural network is this. Yeah.
Looks to me that you're using separated representation of the sort of trying to feed sums of products into the data. And you get a function.
I'm not trying to fit any specific thing. This is a very generic neural network, right? It's some sort of ReLU thing.
Right, but within this example, if you were to do it, and we did it at some point, you will get perfect result.
You would get fine, yeah. You can do this. I'm just saying that this is a very generic kind of method, right? But you could do this. It will work here. Any other questions about this? In some sense, I think this is key. Like this is, well, a key, maybe, not the key, but yeah.
Maybe I didn't get the entry neural network node, the one that is 0.13. To what corresponds?
Yeah?
The 0.13.
The very end. The no filter.
Yeah, that part I didn't get.
It just fails. Without filter, it fails. It didn't fail before because I had 4,000. Here I only have 500. 4,000 is good enough. 400 is not good enough. 500 is not good enough, right? That's it. So without a filter, even neural network is powerless. Yeah.
So why NFM instead of just W1? Like, why is it?
Oh, W1 is not the right size. It's not the transformation of the input. Otherwise, you would be transforming to whatever, the width of the neural network.
But notice the W is NFM followed by an orthogonal transformation, right? So.
Yeah, you could do like instead of eigenvectors, you can take singular vectors. It would be the same. Yeah, you can rewrite it. But I think this is maybe, first it's a little cleaner, I feel. Second, it leads to another algorithm, which I think harder to get the other way. Yeah?
I think of this kind of as a whitening, like it learns the whitening
No,
transformation.
it's not whitening. It's whitening would be normalizing variance in all directions. You're kind of getting rid of those. It's really like PCA, but it's a PCA which is task dependent. Like you want to get rid of those directions which don't affect your output. Mm-hmm.
Question.
Uh-huh.
I mean, so what this seems to me is analogous to is you have 10 quantities which are important and 90 quantities which are completely unrelated to the problem. And so when you do some kind of kernel method, of course, most points that have the same result are very far apart. And so you're not going to, you just can't expect that to work. And I'm assuming that what you're picking up in the NFM rather than the P10 is just the extra information about this quadratic relation that once you know that, you can do a little better. But
actually, you don't have 10. You really have 2.
no, I understand.
Which are important.
I understand this too, but there, of the pieces of information originally flowing in, there are 10 that are relevant and 90 that are not.
True.
Then you're reducing to this two-dimensional thing and realizing it's quadratic. I mean, that's the extra information that in principle is making it work better. But
you can say it that way. You can say, well, you have 10 which are relevant and 90 which are completely irrelevant. And your first goal is to get rid of all the irrelevant stuff because they're just confusing us. And then even within this 10 relevant, you realize that there are actually only 2 which really matter. This is not rotational invariant, but I will show you in a minute an algorithm which has the same form and is rotational invariant, and that wouldn't care about the orthogonal transformations. So it would be able to directly select those 2. Yeah?
Like, isn't W1 only task specific because it's not just one task? Like if you had several tasks, what would you do?
So what we do in practice, we actually just average them. That seems to work. In principle, you could just do them separately, but we've been averaging them. It may be suboptimal, but it works, yeah. So let me now, okay. So one kind of obvious observation, if you just look at this, right? These two look very similar. So that was what we made this conjecture, effectively. We call it non-sats. Basically saying that these two things are the same, and there is some reason to put power 1/2 here, but I don't want to discuss this. We sort of conjectured this as This is joint work which I did with Krishna, Daniel, Bigelho, and Party Pandit, very recent, just this year. So we verify this on actually a lot of different data sets and different architectures. That seems to be nearly universal for like pretty much all architectures and data sets that we can sort of reasonably check, including transformers. But let me maybe take, I don't want to talk about that specifically, but what does it suggest? Well, if this, and you can also do it for deeper layers. This is just for the first layer. You can kind of play the same game in deeper layers. But let me sort of, I want to talk about emergence. And if you think about it, well, what does it suggest? It suggests that AGOP and this W kind of play the same role. And in fact, what we have seen is that this W is kind of an imperfect approximation to AGOP. Like usually AGOP gives you better result than W. They're similar, but so when I say this approximately equal, that's exactly what I mean. They're like correlated with like 0.9 correlation. They're not the same. Yeah, so what does it suggest? Well, if you take this seriously, this actually suggests a very practical model, like neural networks, like kernel machine plus some sort of relevant feature learning, right? That's the intuition that I proposed. Well, that means that I need to learn some transformation of my data and run some kernel on top of it, right? Well, how would you do it? Well, a kind of very basic thing is that you start with your data, you build a kernel predictor, compute this transformation matrix because it's AGOP, so it has this explicit formula that you can write down. It's a bunch of derivatives. Plug this in, transform, filter the data, and then rerun this. Okay? So it's a very simple algorithm. We call it recursive feature machine. Any questions about this? Could that suppose to do this feature learning, similarly to neural network? Yeah.
How does this compare to? I remember reading some things where people talk about you're changing the kernel itself as you go through training. You're trying to align the eigenspace with the kernel in some sense with your target function. Does this have a kind of analog to that, or is it just a?
It's doing something like that. So this is, in general, the idea of learning a kernel is not a new idea. This kernel alignment, for example, actually was considered like, I guess, maybe 15 years ago was pretty popular. This is like a very specific way of doing this. And I don't know why. So the weird thing here is that it didn't work back in those days for some reason that well. Like you got some result, and now it works. And I don't know why. It's like neural networks also didn't work that well, and now they work like, who knows? Yeah.
When you select the kernel, depending on distances between points, you have to select different kernels, right? If you put points very close, you have to have sharp kernel. If they're far apart, you need to have flat one. How do you handle it?
So there are like a bunch of heuristics. None of them are like, yeah, it's like hand waving. But here is one actually very good heuristic. Laplace kernel seems much more robust than Gaussian. So in a lot of actual practical things. So, but by the way, I should point out, this works very well in practice. This is like state-of-the-art on tabular data, this algorithm. Again, this is not something I'm going to discuss. It's in our paper. But the Laplace seems much more robust. So like choosing the bandwidth for Laplace kernel is much less painful than for Gaussian. So that's why we the results are similar.
Okay.
But the selection.
Well, you can take Laplace and represent via Gaussians.
Yeah, it seems that like choosing Gaussian just right is about the same performance as Laplace, but Laplace is just less painful.
Yeah.
Okay. Yeah.
Do you get intuition why that is the case? Like, why is Laplace so much easier than Gaussian?
Yeah, it's tails a bit, right? Gaussian decays very quickly, right? It's a square. Laplace doesn't have a square. It's the best I can do. Yeah.
Could it be beneficial to add a PCA step after the second step? Well, you already remarked on that, but to explore the fact that M has low rank somehow.
Somehow it gradually finds this low rank, and by choosing this alpha, you can kind of control. So in practice, like this alpha, usually we take it 1/2. Well, it depends. Like you can play with alpha, and alpha somehow is a spectral filter. Right? The higher alpha is, the more filtering you do.
Yeah. It might also change geometry of the data once you apply it. If you just do projection, then hopefully it's not going to change the geometry way too much.
You probably don't want to take like alpha super high because this estimate is not very robust, at least initially. So you probably want to be a little bit conservative. Well, like we usually take 1/2. That seems to. There are some reasons that 1/2 may be good in some case. Actually, when the thing is linear, we have a very nice description of this. You can theoretically describe it. It's related to this algorithm called iteratively reweighted least squares. So actually, for the linear case, we can show that when this kernel is actually a linear kernel, so it's a very special thing, it's equivalent to some form of IRLS. And for that one, we actually know what the fixed points are. Yeah? Oh. Yeah.
Using the, okay, does using the filter methods get rid of backprobbing approach?
There is no backprop here at all, right? There is no, it's a completely different algorithm from neural network. This is solving linear system, and this is just matrix multiply. So it's like linear system matrix multiply. Oh, well, you have to get M, which is like basically taking some derivative. So everything is explicit. There is no backprop. There is nothing implicit here. Everything is explicit. It's actually a little bit it's kind of like expectation maximization. You just like repeat these 2 steps, like with the EM. Or even something like K-means clustering has this kind of, yeah?
In practice, how accurately do you have to solve the first step for it to work well? So in terms of, because that, in my head, that could be quite expensive, so solving it to a very high degree of accuracy, that least squares problem. If you take some iterative approach, maybe you could.
We can, like for smaller problem, we just solve the linear system exactly. For a larger problem, we have some approximations. We haven't studied too deeply how well, but we have these iterative methods which can even solve it for like 100 million data points, even something like that. You can scale it quite far by solving this iteratively, the system. This is the problem. Yeah.
Correct me if I'm wrong. Does it mean that you basically find local directions? Because Taylor expansion can be thought as a separated representation if you choose directions correctly. And then you plug it back in.
Yeah. It's some form of manifold assumption, but except it's very weak. It's just saying, okay, like all linear directions are kind of roughly aligned, right? It's like a very weak form of a manifold assumption.
You need to align.
They somehow need to align. And why do they align? Well, who knows, but they seem to align. And you can sort of argue that maybe low rank is reasonable because many problems probably depend on just a few things, right? But why don't you need some nonlinear? I actually suspect you can do better by like doing some sort of local alignment instead of global alignment, but this is what we have at this.
But more or less it's a rotation.
Well, it's a projection.
Projection, but you know.
Yeah, yeah. Yeah.
So how much is, so I mean, okay, so a big part that you're suggesting is the selection of important variables and then the linear recombination of those, but part of the story of deep neural networks, and in particular the depth, is that it's about nonlinear combinations. You get one variable that's a cutoff that's combined with another that's a that there's a whole bunch of nonlinear combinations that basically discover unusual features. Like a cat face feature that lives at the end of the space that feels it's kind of hard to think of that as just a linear combination of input directions rather than a set of nonlinear cutoffs. But is this saying that feature generation is less important than the feature filtering and the linear combinations?
So this is kind of a slightly strange algorithm, maybe. So what you do, you not just like you take some sort of nonlinear predictor, but then you forget about it. You just extract this matrix M. Then you use it as a filter. So you're extracting some linear thing from a nonlinear, and then you repeat it. And after the last step, the final predictor is what you use. And that thing is nonlinear. But it's, if you think about a neural network, it's kind of a neural network if you wish, but it's a very simple one. So what I'm saying is that it looks like a lot of magic is just this one linear transformation and then some nonlinearity on top of it.
But the fact that you're doing it recursively also generates all these features effectively.
It generates
so it's hard to say which it certainly does not separate between whether it's filtering important things, combining linear features, or combining linear and nonlinear features, because all those are present in this operation.
Because this a filter you get from some sort of nonlinear combinations, right? But the final form of it is just a linear transform followed by some sort of nonlinear thing. And I would argue that at least with MLPs, this is basically what happens. Mm-hmm. Yeah?
So say you know the true F. So then there are level sets for F. And what this works well for us if those level sets are essentially linear. But let's say F is the square of the distance from the origin. So then it's not, M is going to be everything, and you won't get anywhere. So it's like, if I could say it, it's like instead of when people try to detect dimensionality of a data set in Rn, you're trying to detect sort of the linear dimensionality of the fibers.
Yeah.
And of course you could, I mean, for sets of Rn, they often do this at, linear approximators in different places, and you might conceivably be doing that with this and get somewhere. The other thing is, I mean, a random projection tends to preserve a lot of the distance information, and so that aspect of it.
You don't want to preserve distance information. You want to kill distances along directions which are irrelevant. So if you think about it, this is so imagine like this is my one, like this one direction which is important. All of these directions are not important. Now, if I'm computing distances, because of Pythagorean theorem, I'm summing up all the stuff which is not important. If I somehow just know that this is the only important direction, right? My fibers are linear. This is a lot of information. So that's what I'm kind of assuming. That's why I said it's some sort of weak manifold or some like linear, I don't know what you would call it. But yeah, you somehow, you could say, well, let's see. You will see. It's kind of, it actually has some magic. Just this thing already is capable of pretty amazing stuff. Yeah.
How does this scale in terms of compute or speed or memory if you make it deeper?
This is solving a linear system n times n. This is pretty cheap. This is the number of features. As long as your number of features is not too large, this is cheap. So this is the main thing in most cases. But you can solve quite large. You can solve it for very large systems if you want to do some sort of approximation. Actually, we can take it offline if you're curious how to solve it. I could tell you a little bit how to solve it for 100 million data points. Yeah.
So, since as you mentioned, you can interpret the sort of final stage of this process as a kind of weird neural network. I guess it would be like an infinite neural network. Can you, if you were to look at the training trajectory of that infinite width neural network as you were training it via backprop, is that shadowing what's happening as you do this process of, do the kernel predictor, then do the AGOP, then filter? Are you getting sort of an aligned thing in those two different semantics as you were?
Yeah, so the argument here, I'm sort of not going to fully substantiate it, is that this process is actually very similar to how MLP is trained. This whole process, not just the last one. Even though it's obviously not at all in details like that, but much of what you see, much of the interesting things that you see in neural network, you can see here. And it's also a practical algorithm in its own, because it's own merit. But let me show you. Okay, let me do a specific example because it's kind of cool, and it will sort of pre-shadow emergence. This is like baby emergence. Okay, so what is this data? The data is just two types of images from CFAR10. This is what CFAR10 data looks like. It's images like this. I have just two classes in this case, trucks and planes. And there is like a little shape, a little star embedded, and the color of the star just encodes the classes. So we will just put like this little star there. So if you know to look at this little pixel, you can solve the problem. It's trivial. If you don't know, look here, there is a lot of variance in this image. It's a pretty hard problem. Okay, so let's see what happens. Now, this is an ordinary neural net. I don't remember, 2-layer, I think, maybe more, MLP. And let's see what happens. So you see, after about 90 epochs, the training accuracy is already 100%. But you can see that the test accuracy is like 80%. Which is not that good. And you keep training it, and you can see that the test accuracy, the training accuracy is always at 100%. Well, it doesn't get better than 100%, but the training accuracy, the test accuracy gradually improves. So that's exactly this kind of phenomenon we saw before. Now, like, why is this happening? Actually, it's not that hard to see what's happening, because if you look at this feature matrix, you can see that this little star is gradually emerging, and it's becoming more and more clear, right? It's kind of pretty noisy here, much cleaner in this case. All right? Now let me compare this to what happens in our method. In our method, kind of the same thing happens, but it's much quicker. Now, after 0 iterations, so that's with 0, I just apply the kernel once. You can see that the accuracy is only 55%. It's just a little bit better than random guessing. Random guessing, of course, would give you 50. But you can see that the star is already very clear. After 1 iteration, you get 90%, and after 2 iterations, you get perfect. So what is happening is that it's learning this feature matrix, and once you learn a feature matrix, you get rid of these extra variables. You get rid of all the stuff. You see, okay, these are the only pixels I have to know to predict this. Let's get rid of all these planes, trucks, all that nonsense. Just look at the star. So that's what it's figuring out. Now, okay, you can ask, well, what about the loss here? These are all trained to have loss exactly 0. So the loss here is identically 0 in this case. So that completely decouples any influence of loss onto the feature learning. Okay, any questions about this?
A silly question. Why is the accuracy at 100 at 0 iteration?
Oh, because we just fit the kernel to fit exactly the training data. So the training data, at every iteration, your loss is identically, well, numerically 0, machine precision. But of course, the test loss, right? It's the test accuracy is pretty bad here, much better and perfect. So you can kind of see that this is somehow similar. Like the process appears to be the same. We have much more, other examples to show that they're really similar, but this is like one. In this, we'll go into this Grokking thing, which I'll discuss in a minute. Okay. Now you can say like feature learning in neural networks is distinct from fitting the training data, right? This is not learning by fitting the training data. This is learning by doing something quite different, by this feature learning. Now this, of course, is a combination of two, because you can never have loss 0 in this case. Otherwise, you wouldn't train. So RFM decouples feature learning from optimization. And then, and this is unfortunately doesn't work, but that's what I hoped for, is that you can say, well, AGOP rank should be a progress measure, right? Because this is a low rank, it has a low rank solution. the rank of the actual predictor is just 1, right? You just need to look at 1 pixel in the end. So we can look at the rank, and rank gives us something. Well, that's what we can hope, at least. OK. Now let's look at this thing. So this was baby Grokking. So you see why I call this emergence, because, right, you have like 100% here, and you get something here. That wasn't like terribly surprising to me in some sense, because, OK, we already know that very big neural networks do well. It kind of stands to reason that maybe you can keep training even after the loss is very small. But let's look at this. And first, let me tell you how this data is encoded and what exactly the problem is. So basically, I'm giving you the multiplication. Well, in this case, this is division, but I'm going to talk about it. Doesn't really make a difference, but most of my examples are with addition. So with addition, basically, I'm giving you a table like this, right? And effectively, what you want to fill in the missing entries in this matrix. So how do I get the input? So let's just do mod 3 arithmetic, so you can see how it's encoded. 1 would be, so it's one hot encoding, so 1 is encoded by this, 2 is encoded by that, 0 would be encoded by 1, 0, 0, OK? And so if 1 plus 2 equals 3, you give it as input this vector. It's just a concatenation of these two encodings. As an output, you give it whatever the result is. So it's a pair. So in general modular P, we have P squared examples of addition and P minus 1 squared examples of division, or P times P minus 1. And we use like, say, 50% for trading, the rest for testing. OK, now let me show you what actually happens with RFM. So you can see for the first 10 iteration, my accuracy actually is just at random. And now you can look at the loss, and you can see that the training loss, of course, is identically 0 because I'm just fitting it exactly. The test loss doesn't change at all. And remarkably, after about, whatever, 11 or 12 iterations, it just very quickly transitions to 100%. And you can see that the loss is a little smoother, but it basically undergoes the same transition. So now this is exact emergence because, well, I don't even see like slight improvements here. There is no improvement at all. So like no signal comes from this. Nothing comes from that, right? This is exactly what they see there, except now decoupled loss is identically 0 in training, so that's fully decoupled. Okay, any questions about this? Yeah. What's that? There is no regularization here, but yeah, you can, yeah, I think this particular thing, no regular. You don't need regularization.
I think I don't understand. You're saying this is gradient descent with...
There is no gradient descent.
Okay.
This is RFM, right? This is you fit a kernel, compute the
sorry.
transformation matrix. There is no gradient descent anyway.
That makes more sense.
Yeah?
I don't know much about kernel fitting, but is there only one kernel that would fit your data?
Oh, this is with Gaussian kernel. You choose a kernel is somewhat arbitrary choice.
If you chose
you
a
can do
different
quadratic
one,
the same way. Quadratic and Gaussian work the
and
same.
if you chose a different one, you would also see emergence.
A good question. Laplace doesn't work for this case.
Why?
I don't know. It's actually, it kind of prevented us from getting results on this because for a while, because for everything else we use Laplace. For this one we use Laplace and we saw nothing. And so for a while we just thought it doesn't work at all. Like we couldn't get Grokking this.
That's very strange.
Yeah.
Very strange.
Because you can take Laplace, represent it via Gaussians. No, you cannot do the reverse. Or maybe you can.
It basically we couldn't get it to work. I don't know. I cannot say anything really. I can maybe say something stupid about this, but I probably shouldn't. Huh?
Maybe it was a bug.
Very unlikely. It does a lot of experiments. So very unlikely to be remarkable.
Strange.
Do you think that's due to the gradient term? Because Laplace, said the gradient gradient.
Laplace somehow doesn't it's a slightly different shape, right? But I don't know. Maybe I shouldn't say stupid.
Gaussian, that's gradient is fine, but the Laplace gradient will pick up.
No, because you see, for everything else, Laplace works just fine. So, like the fact that it has this kink at the top really doesn't matter. Yeah.
Is this image data?
No, this is this data. It's this.
So you have sequences?
The input is just you can view it as in fact, the first paper used a transformer for this. So that thing was doing a transformer. You can view it as a sequence of 2, right? It's actually not that different from, like text things. So you can, this is talking 1, this is talking 2, and the output is talking 3, which is the addition of those 2 tokens. But we don't use it as a sequence or anything like that. We just give concatenation of these 2 things.
That's what's confusing to me, because anything that's sequence-like, Laplace does better for than Gaussian, and anything that's like image-like Gaussian does better, so I'm a little confused of why.
I really cannot say anything intelligent about why Laplace doesn't work and Gauss works. More research is needed. I think for pretty much every other task, Laplace works at least as well as a Gaussian.
Other than just this one?
Other than just this one. So, I don't know. It's confusing. There is probably a good reason, and it's probably something simple. Yeah.
So does the AGOP rank change in that period?
I'll talk about rank in a second.
Is that continuous?
Let me show you the AGOP, actually. Okay, I'm now going to show you the AGOP of the thing. Can you guess? Can anybody guess what it is? If you haven't seen the paper, of course. Otherwise, it's not very interesting. That's overfitting. Anybody can guess what the AGOP is going to look like? Huh? So I'm going to plot the AGOP matrix. So this is modular. Well, for example, rank. So AGOP is going. So this is like modular addition mod something like 60, whatever, 67 maybe, I forget. So it's going to be like a matrix whose size is 2p by 2p when p is it's addition modular p. But what is it going to? What is the matrix going to look like? Well, this is what they look like. So you can see it becomes this kind of striped. So this is because it's 2p by 2p. It has these 2 blocks. That's not really surprising because it has this input structure. What is surprising?
God, that's
We'll get too close, Mark.
You have a question on that.
Go ahead.
Yeah. So the question is, just from the neural network perspective, or from this perspective also, once it reaches the grokking stage, does it stay there, or do you have the test again dip? Like, essentially, what is the structure of the region of grokking?
The region of grokking.
Yeah, like from the neural network perspective, you have certain weight vector regions where the...
We don't have this, right? This is not a neural net. This is a quite different setup. So, yeah, I don't know what it means. Like, it's not a neural network, right? We don't have initialization. We don't have anything. Like, we don't have gradient descent. So I'm not sure it sort of makes a lot of sense to say what like in our setting. So I think that's a kind of nice thing about our setting, because like a lot of things which are specific to neural networks disappear, and it's like, yeah. Circulant or whatever that is, Henkel. It can be also Henkel, but this is circle. This is actually circulant. Yeah. So basically, the diagonal constant is it's constant on the diagonal, so it's toplet, but it actually wraps around. It's actually circulant. So, what's that? Well, I don't know. I mean, we don't understand why it becomes this way. It's not clear. It somehow learns. It learns some sort of Fourier transform, but like why is it learning? I don't know. Well, it makes sense that you have some sort of dependence on this, but why is it doing this? I don't know. It's like why is this? So you see, I would expect that it doesn't work at all because any reasonable early stopping process here would say, okay, you're not learning anything. Stop after 5 iterations, right? You're just wasting your time. But if you have patience or just like, like distracted, then you like run it longer and suddenly it learns. So I don't know, like how does it decide that this is a good idea to learn this, given that there is no signal here, right? There is no prediction. The prediction is just trivial.
Well, but I mean, at that point, presumably you've sort of stopped learning the W matrix, so to speak, in your previous terms, right?
Like here somewhere you stop. Yeah, at the 15th iteration, you kind of stop learning.
And at that point in time, what you're doing is you now have learned your embedding, right? So you're embedding into some sort of a specific dimensional space, and you're doing just kernel learning on that space.
Yeah. Once you do something like that, you can see that something like that would be not a bad idea.
Like motion, and there it only depends on the difference between the two
variables. Yeah, that's true. That's what you mean. Okay, yeah, makes sense.
And that kind of explains the stripes.
Well, no, it explains why the stripes would work if you knew to get the stripes. You see, this is a post hoc explanation. Like, if you know that it's doing something like that, then of course stripes would be a reasonable choice. If you don't know a priori, why would you learn this? But you can see it's learning the stripes. Even the first one already has some sort of notion of the stripe. So it's learning very early, but there is no signal. That's... But it's coming from me fitting the kernel, but that kernel is just predicting everything at random, it seems. So clearly it's not just doing this, but like at least from this perspective of the loss, I don't see anything. That's why I'm saying it's kind of like a butterfly appearing out of cocoon. Clearly something is getting rearranged inside, but like I'm only observing this. I don't see where it's coming from. Like somebody smarter with X-ray vision, right, can probably see that. That's what it has to do.
This has to be fully analyzable.
I agree. Yeah.
If you're using Laplace, how would the AGOP change?
We haven't looked too carefully at Laplace. In fact, that's kind of, we need to look more carefully. I suspect we still learn this, but for some reason it doesn't quite work at the end. Something
Will that
somewhere.
denoise it or something? Are you saying the next steps are not going to work?
Possibly. I would need to look carefully. I asked one of my colleagues. This is, I should say, this is very recent joint work with Neil Malinar, Daniel Picklehall, Libin Zhu, Adit Radhakrishnan, and Parthi Pandit. Yeah?
Yeah, sorry. Very cool. I was just wondering if you looked at any other kind of maybe see how these types of matrices coincide with any form of implicit regularization. Like, is there some, over time, are you also minimizing something like some norm of the kind of AGOP matrix, for example, something like this, which just, when it's also fitting the solution, coincides with these kinds of segment matrices? Is that something you observed, or like that?
It's not clear. So at every iteration, kernel fitting you can view as minimizing some norm, the fitting itself. But this AGOP is not clear what it corresponds to. There is some sort of neural network norm which you can kind of view as doing something similar, but again, it's not clear. And even if it's coincides, it's not clear why it would learn. Let me actually get to the neural network, because I'll show that neural network does something very, very similar. But this is, I think it's pretty mysterious, and the kind of shocking thing is that this is such a simple thing. And we're already, like, if we cannot figure out when to stop this iteration, how can we figure out when to stop GPT, like 9.6 before it like kills us all or something? Yeah.
So when you generate these strings, you use a modulo 3 operation, no?
Not modulo 3. 3 is just an example. Modulo like 101 or something. In this case, 67, I think, something like that. Yeah. 3 is too few examples. Okay, let me now let me point out one more thing. So this is for addition. Now let me show you one for multiplication. So first, let me tell you it works. It also works very nicely. This is a final AGOP. Okay? This is what it looks like. Any guess what this is? Yeah, kind of, yeah. Looks pretty random, right, if you just look at it like this. But let's think about multiplication, right? Modular multiplication is, is z over pz star, right? This is a prime, so it's a cyclic group. And that's a, we can take discrete log, and then it becomes addition, right? So yeah, it is exponential of addition. Once you rearrange according to this. Oh goodness, this is terrifying. It's like it's coming for me, definitely. Like it doesn't like this. We're getting into its secrets.
Somebody online wants to ask a question should raise their hand and keep it up. Because you're muted the moment you lower your hand. So if you have a question, just raise your hand and then speak.
Okay.
Yeah, just wanted to say discrete log, but because you already said that, I lowered the hand.
Oh, okay. Okay, in any case, so if you just rearrange this with respect to the multiplication, the generator, this is what you see. So, okay, this is, on one side, this is beautiful. We have some sort of fairly simple mathematical insight, right, that you can take log. On the other hand, this is terrifying. Because if you just look at this, you see nothing. At least I see nothing. Maybe you see something. But so you need to have this mathematical insight that this group has is generated by a single element. Now, okay, for z over pz, this is a very basic mathematical fact, right? Like maybe take some group theory. It's like a basic thing. But what if something like that happens for something more complicated, right? Like I don't think it would be very difficult, I think, to sort of have this kind of insight for anything much more complicated than that. And then you just wouldn't see it. In any case, so there is this hidden pattern. Now let me discuss some measures. So the standard measures of progress basically tell you nothing in this case. But let's look at something maybe once we know kind of post hoc that this is learning the circulant matrix. Well, you can say, okay, well, can we look at how different my matrix from a circulant matrix? Well, a circulant matrix has constant along the diagonals, right? Along diagonals, wrap diagonals. So you can look at the variance along those diagonals. If the variance is 0, then the matrix is circulant, right? So it's a natural measure of not being like deviation from a circulant. And if you look at the circulant deviation, you can see it's kind of linear, right? So it starts learning very early and it just like continues learning until it basically just kind of does it.
You can use displacement rank.
What's that?
Displacement rank.
Is that, I don't know what
I'll explain.
Okay.
Chomplets matrices have displacement rank 2.
Oh, I see. So maybe, yeah, we can maybe use that as a measure of progress. We just looked at the variance. It's kind of straightforward. Now, you can look at another measure of, you can look at AGOP alignment to see like what AGOP you have at certain point and just the cosine of the angle between matrices. And you can see that, yes, AGOP basically is just like linearly, you're converging kind of linearly to the final AGOP of this thing. So notice neither of this is very satisfactory, because of course AGOP alignment is kind of, it's telling you that you're converging, but you're converging to what? You're converging to that solution that you would get in the end. So you somehow have to know solution in the end to even be able to say anything intelligent about it. This is even worse because circular deviation, okay, it's very satisfactory, it's very clean. The problem is you have to know it's a circulant. And like even for this rewarded circulant, unless I know to reward it, I wouldn't be able to tell that it's a circulant, right? So if you don't have that particular insight, you wouldn't be able to measure this at all. Okay. Now the question is it just a circulant or there is some sort of other structure there? And the answer is pretty much it's just a circulant. So you can initialize this matrix with a circulant. Just throw a random circulant at it. How do you make a random circulant? Take a string of random numbers and just rotate it a bunch of times, make a circulant matrix. Turns out if you use that and put a kernel on top, it learns perfectly. So doesn't look like there is anything more than a circulant going on. If that's your insight, that's enough. Yeah.
I'm wondering how would this method work if you randomly flipped some bits or like appended maybe noise to the sequence 1, sequence 2, and then sequence 3 is like some random noise?
We have not tried the noisy one. I don't know. Actually, that's something we're trying now. But I haven't, right now I don't have any, like how fragile it is, I don't know. Yeah, so that's basically, so the random circulant basically works very well. You don't need to learn the circulant, you can just like guess that it's a circulant. Okay, now let's look at neural networks. And this is now for neural networks. This is AGOP, but for neural networks. And you can see it's either a circulant or Hankel matrices. Well, Hankel is just circulant the other way around, like opposite direction. Circulant is diagonal and Hankel is anti-diagonal. And you can see they're a little noisier, but it basically looks the same. Now you can look at the what's happening with accuracy loss, and you can see it's very similar to what we observed for RFM. Now, if you look at the circular deviation, you can see that it's actually also like pretty much linear. Like there is like a little piece where it seems to be constant, and then it like linearly improves. And the same thing with AGOP alignment. So it's a very similar behavior. So it doesn't look like neural networks are doing anything weird. Or they somehow know that they want to learn a circulant and they just like learn the circulant. Like how do they know it? I don't know. But like I guess like every update that you get a neural network gets you like a little bit closer to the circulant. So now the question is, that was to me the question like, okay, is it low rank? Because I somehow thought that low rank is so reasonable and it has a lot of sort of nice interpretations. And the answer is that thing is not low rank because circulant is not a low rank matrix. It's full rank, more or less full rank.
It's displacement rank is low. It's a different measure.
I would like to discuss the displacement rank. Maybe we can make some conjecture because.
Think of the following: you shift the matrix a little bit by one element and subtract.
Okay, that will be low.
Diagonals will disappear except for one row and one column.
I see.
2 rows and 2 columns.
So, but how do you?
That's a commutator with the shift.
Yes, exactly.
But how do you know?
How much you commute with the shift?
Yes.
So here is a kind of strange thing to be, right? It looks like this method can learn low rank matrices, or it can learn low displacement rank matrices. So what's the convex span of these things? What kind of so clearly it needs some sort of structure, right? And some maybe low rank structure, but it cannot be just like regular low rank, right? Because of the displacement rank. So what are the kind of structure that this thing can learn?
So you know what it could be? This notion of taking a commutator, right? It is some kind of a derivative. I mean, in this case, the shift matrix with which you take a commutator somehow represents your problem, the fact that your addition is
So there is somehow
invariant,
symmetry,
right?
yeah.
So somehow on your, I don't know, on your manifold of things of data or something like this, there is some thing that lives, and taking the commutator with this is like taking a gradient, and what you're saying is that that gradient is low rank.
But why is it looking at the, what else can it look at, right? I guess what is very puzzling to me that clearly this is a very structured problem, and the sort of standard low rank is also very structured. And I sort of kind of convinced myself it learn ordinary low rank things, and we're observing that it can learn this. But what else can it learn?
What I'm proposing is something like this. Imagine you had your manifold of data, and on that manifold you had some kind of a flow. So you could just move along data. So that would be like some vector field or something like this. The commutator with that, so the derivative along that thing of your AGOP matrix would be small, or would have small rank.
I see. Well, maybe we can discuss. I would very much like to formulate some sort of hypothesis like that. But yeah, so let me continue. So yeah, basically with neural network, it looks like it's very similar with neural network. Now, actually, this is a weird thing because there is an implementation of this which is low rank, just low rank. And it's very simple. Maybe I don't want to explain because it's I'm out of time. But there is like a rank 4 implementation of this. So like before we did it, I was like, okay, of course it's finding this rank 4 solution. The solution, you just like map it into complex numbers basically. And you have a quadratic form which does multiplication in complex numbers. That's a rank 4 if you write it down. But it's not what it finds. It finds this other thing, which you can view as some sort of Fourier transform. The thing is effectively Fourier transform. So why is it finding that and not the actual rank solution that exists? I don't know. So, okay, maybe I'm out of time. So maybe let me just kind of give you like a few thoughts about this. I was thinking like talking about optimization, but I'll just skip optimization. Nice as it is. Okay, so first, this circular feature is kind of Fourier multiplication algorithm. This is very interesting also because this is an out-of-domain generalization. So once you learn the Fourier multiplication algorithm, you can apply the same algorithm on things which are not like 0 and 1, but just on arbitrary real numbers, and it would do something sensible. So it learned clearly out of domain. Not specific to neural network gradient-based methods, so I think any explanation which only explains neural networks is not going to explain this. Not predicting by test or training loss. And I think there is like really strong evidence that there is some phase transition, no sort of clear a priori way to measure this right now we have, and maybe we can come up with some notion of rank. I mean, I'm hopeful. I mean, that would be fantastic. And kind of what process can it learn? And let me maybe a couple of points about the Mirage. So there was this paper, Emergent Abilities of Large Language Models in Mirage. And the kind of basic suggestion there was that sharp emergence may be due to, because we're optimizing something continuous, but we're measuring it something discontinuous, right? Because we're measuring accuracy, which is, like a discrete measure, but we're optimizing something like cross entropy or square loss or something like that. That may well be true in some settings, but this is clearly not an explanation, because here everything is decoupled. So definitely not a mirage for modular arithmetic. Definitely this is like a true phase transition, and something similar has been observed for sparse parity in particular. So now in real practical problems, is this a mirage or not mirage? It's really hard to tell because there are like so many things involved. That's why I think we need to have this like much simpler setup so we can actually understand something. Okay, so I think I'll stop here because there are other stories kind of story on its own.